Number 1. Guizhouichthyosaurus with a Thalattosaur in its gut. The specimen was found in 2010 in the Guanling Formation of Xingyi, Guizhou Province, southwestern China, during quarry work in Middle Triassic marine reptile beds. The formal description was published in iScience in August 2020 by Ryosuke Motani, Daiyang Jiang, Andrea Tintori, Olivier Riopel, and Cheng Ji. The specimen, catalogued as GMPKUP 2000-01, is a 5-meter Guizhouichthyosaurus tange. Inside its rib cage, packed into a single dense bolus, sit the vertebrae, ribs, limb girdles, and partial limbs of a Shinposaurus xingyensis Thalattosaur. The recovered torso measures about 1.2 meters, but the original prey would have measured roughly 4 meters from snout to tail. The body length ratio of prey to predator approaches 0.8 to 1, the highest documented in any vertebrate fossil ever found. The prey's head, neck, and tail are absent from the gut, indicating the predator bit it cleanly in two before swallowing the larger half. Bone surfaces show no significant acid etching, meaning the predator died within hours of the meal. The deposit dates to the Anisian-Ladinian boundary, approximately 244 million years ago, during the recovery period after the end Permian extinction. Guizhouichthyosaurus has blunt, peg-like teeth without serrations or cutting edges. The mainstream interpretation had been that such teeth indicated grip and suction, feeding on soft prey like squid and small fish. The Shinposaurus inside the stomach demolished that view. The cervical vertebrae of the Thalattosaur show stretching and distortion consistent with violent tearing forces. The predator gripped the prey and shook it apart, much as a modern killer whale dismembers a sea lion. Stable isotope analysis of Guanling marine reptiles confirms that ichthyosaurs of this size class held a high trophic position. Some paleontologists have argued the meal itself killed the predator, perhaps by neck rupture or asphyxiation. A more conservative interpretation holds that the predator died of unrelated causes shortly after feeding. A speculative view suggests the act of macropredation in such a recently evolved ichthyosaur lineage was inherently risky and fatal more often than not. Whatever the cause of death, this is the earliest known case of true marine reptile macropredation, predating the Jurassic Pliosaur radiation by tens of millions of years. The fossil is housed at the Geological Museum of Peking University in Beijing. Number 2. Sinocalliopteryx, the feathered predator that hunted other feathered dinosaurs. The genus Sinocalliopteryx gigas was named in 2007 by Ji Xuan, Ji Chang, Lu Junchang, and Yuan Chongxi from the Yixin Formation of Liaoning Province, northeastern China. The species was a wolf-sized compsognathid theropod, 2.37 meters long, 18 to 20 kilograms in mass, with long filamentous protofeathers covering its body. The genus name means Chinese beautiful feather. A second specimen, catalogued as CAGS IG 20009, was described in 2012 by Lida Xing, Phil Bell, Philip Curry, and colleagues in PLOS 1, and the gut contents were unprecedented. 2 Confuciusornis sanctus birds, primitive toothless avians with long tail streamers, sat partially digested in the stomach cavity, their articulated foot and leg bones still in place. Alongside them lay the partial remains of a Sinornithosaurus, a small feathered dromaeosaurid roughly the size of a modern raven. A feathered theropod had been actively hunting and eating other feathered theropods, including its own distant cousins among the dromaeosaurs. The 2 Confuciusornis individuals appear to have been consumed within a short window of each other, indicating gorging behavior, perhaps a roost raid in the manner of a modern goshawk striking sleeping birds at night. The prey leg bones show partial gastric etching, confirming digestion was underway when burial occurred. The Yixin Formation is dated to roughly 124.6 million years ago in the Aptian stage of the early Cretaceous. The lake deposits preserve volcanic ash layers that fossilize the Jahal biota in extraordinary detail, including soft tissue, feathers, and gut contents. This is the only known case of a non-avian dinosaur preserved with multiple bird species in its gut, and one of the only documented cases of intergenous predation among feathered theropods. The skeletal completeness of the prey items rules out scavenging. Sinocalliopteryx was hunting actively, swallowing prey whole or in large pieces. Some researchers argue this evidence makes Sinocalliopteryx the closest functional analog to modern raptors among non-avian dinosaurs. A minority view holds that the prey may have been pre-killed by another predator and fed on opportunistically, though the gorging pattern of 2 birds in one gut argues against this. Sinocalliopteryx is closely related to Compsognathus from Jurassic Europe and Hoaxognathus from the same Liaoning beds. The holotype is at the Ginsu Paleontological Museum and the gut contents specimen at the Chinese Academy of Geological Sciences. Number 3. Prognathodon, the mosasaur with a 4-species buffet in its stomach. Prognathodon overtoni was first named by Williston in 1897 from Pierre Shale specimens collected in Kansas. The most remarkable individual in the genus's history was unearthed in the Bear Paw Formation of southern Alberta, Canada, and catalogued as TMP 20007.001. Takiya Konishi, Michael Newbury, and Michael Caldwell described it in PLOS One in 2014. The mosasaur measured approximately 6 meters in length and lived during the late Campanian Maastrichtian, around 74 to 72 million years ago. Inside that single stomach cavity sat the partial remains of 4 entirely different prey species: a sea turtle, a teleos fish, a probable smaller mosasaur, and the shell fragments of an ammonite. The turtle is identified as a chelonioid, possibly a young Toxocheles, with carapace fragments and limb bones recovered. The fish remains are diagnosed by characteristic vertebral and scale impressions belonging to a large teleost. The smaller mosasaur is identified by partial vertebrae consistent with a young plioplatecarpine, such as Platecarpus. The ammonite presence is indicated by aragonite shell fragments, possibly belonging to a Placenticeras, a large flat-shelled cephalopod common in the western interior seaway. Bone surfaces show beginning stages of acid etching, suggesting hours of digestion before death. Prognathodon's robust conical teeth made the dietary breath possible, while more gracile mosasaurs like Platecarpus had piercing teeth specialized for fish. Prognathodon could crush thick turtle shells and ammonite armor with equal ease. Konishi and colleagues propose that the predator may have been opportunistically scavenging some of the items while actively hunting others. Mosasaur stomach contents are exceptionally rare. Across the entire global record, only a handful of specimens preserve confirmed gut contents at all. The Alberta find is the most diverse single-meal record ever documented in any marine reptile. The genus Prognathodon was geographically widespread, with over a dozen named species ranging from Morocco to New Zealand. Some researchers have questioned the ammonite consumption, arguing it might represent accidental ingestion or post-mortem deposition rather than active feeding. The Konishi study addresses these doubts directly, citing the consistent positioning of the shell fragments within the gut bolus. A more speculative view holds that mosasaurs may have ingested ammonite shell fragments deliberately as gastroliths to aid digestion. The specimen is housed at the Royal Tyrrell Museum of Paleontology in Drumheller, Alberta. Number 4. Scipionyx samniticus, the Italian theropod with visible last meal. The fossil was discovered in 1981 by amateur collector Giovanni Todesco at the Pietraroggia Plattenkkalk in southern Italy's Benevento province. He kept it privately for over a decade, unaware of its scientific significance. Cristiano Dal Sasso and Marco Signor recognized its importance in the late 1990s, and their formal description appeared in Nature in 1998. The specimen, nicknamed Ciro by the Italian press, is a juvenile Coelophysis theropod hatched only days or perhaps weeks before its death. It measures just 24 centimeters in body length. The animal dates to the early Cretaceous Albian stage, approximately 113 million years ago. Pietraroggia preserves a rare combination of fine carbonate sediment and anoxic bottom waters, the conditions needed to capture soft tissue and stone. Preserved alongside the bones are dark phosphatic stains marking the position of internal organs. Intestines, liver, esophagus, trachea, and possibly even muscle fibers can be made out in the limestone. Inside the stomach cavity, partially digested vertebrae and scales of a small lizard are still visible. A second prey item, possibly a small fish, was identified during later study. The lizard prey shows acid etching consistent with active digestion at the moment of death. The species name honors Scipione Breislak, an 18th-century Italian geologist who first studied the Pietraroggia deposits. Phylogenetic placement of Scipionyx has been debated. Some authors classify it as a compsognathid, others as a more basal Coelophysis, but its identity as a small carnivorous theropod is not in dispute. Histological analysis of its bones suggests a high growth rate consistent with a warm-blooded metabolism. The preserved soft tissue allowed researchers to reconstruct the gas exchange anatomy, supporting the view that theropods possess bird-like air sac respiratory systems even in their juvenile stages. Dal Sasso and Maganuco published a comprehensive monograph in 2011 that remains the definitive technical study. A minority interpretation has questioned whether some of the dark stains represent organs at all, suggesting they may be diagenetic artifacts. The mainstream view, supported by elemental mapping, identifies them as genuine soft tissue replacement. Scipionyx demonstrates that small theropods consumed lizards and fish opportunistically, predating later evidence from Sinosauropteryx in China by several years. Even very young theropods were active predators rather than dependent hatchlings. The fossil is held at the Soprintendenza Archeologica in Salerno, Italy. It is widely considered one of the most exquisitely preserved dinosaur fossils ever discovered. Number 5. Microraptor zhaoianus, with a severed mammalian foot. Microraptor was named in 2000 by Xu Xing, Zhou Zhonghe, and Wang Shaolin from the Jiufotang Formation of Liaoning, China. The genus contains at least 3 named species: Microraptor zhaoianus, Microraptor jiuai, and Microraptor hangqingyi. Specimens come from the Jiufotang and Yishan formations, dating to roughly 120 to 125 million years ago. Adults measured 60 to 90 centimeters in length and weighed only about 1 kilogram. The animal is a 4-winged Peruvian dromaeosaur with flight feathers on both forelimbs and hindlimbs. The 4-winged glider hypothesis proposes that Microraptor used both pairs of feathered limbs to glide between trees in pursuit of prey. Color analysis of preserved melanosomes by Quanguo Li and colleagues revealed the plumage was iridescent black-blue, similar to a modern raven or magpie. 3 documented gut content cases reveal Microraptor's dietary range. In a 2011 study published in Proceedings of the National Academy of Sciences, Jingmai O'Connor described a Microraptor specimen, QMV1002, containing the partial remains of an enantiornithine bird in its stomach, oriented headfirst as if swallowed whole. A second specimen, BMNH FRDCCLS 20000001, contained an articulated juvenile mammal foot. The mammal is identified as a multituberculate or Eutriconodont grade Mesozoic mammal. The toe bones and claw sheaths remain intact, indicating limited digestion before death. A third Microraptor specimen, described by Lida Xing in 2013, contained fish remains including scales and partial bones. The 3 diverse prey types, bird, mammal, fish, establish Microraptor as a true generalist predator. For an animal weighing 1 kilogram, this dietary breadth is striking. Some paleontologists have proposed that the mammal foot may not represent active predation. Microraptor might have scavenged the foot from a larger predator's kill or fed on a recently deceased mammal. Others argue the articulation and intact claw sheaths point to an active capture. A speculative interpretation holds that Microraptor used its 4-winged glide to ambush mammals from above, dropping silently from low branches. Stable isotope analysis is consistent with a diet that included tetrapods and fish. The species name M. zhaoianus honors Chinese paleontologist Zhao Shijin. Microraptor is the most abundant non-avian dinosaur in the Jehol biota, with hundreds of specimens recovered. The mammal-eating specimen is held at the Beijing Museum of Natural History. Number 6. Sinosauropteryx prima, the feathered theropod with a mammal jaw inside. Sinosauropteryx was discovered in 1996 in the Yishan Formation of Liaoning by farmer Li Yuman. It was the first non-avian dinosaur ever identified as having feathers, formally described by Ji Qiang and Ji Shuan in 1996. The species name means first Chinese reptile wing. The animal was a small chicken-sized compsognathid theropod, around 1 meter in body length, with proportionally short forelimbs. The body of the holotype was surrounded by a halo of dark filamentous structures, which Curry, Chen, and others later confirmed as protofeathers. A second specimen, catalogued as NIGP 127587, contained the partial remains of 2 mammals in its stomach. Curry and Chen described this find in 2001. One of the prey items is identified as Zhaoianus quinquicuspidens, a Symmetrodont mammal, a member of an extinct lineage that diverged from the Eutherian-Metatherian split before placental mammals existed. The Zhaoianus remains include a partial dentary, the lower jaw, with teeth still attached. A second smaller mammal jaw belonging to a different mammal taxon was identified in the same gut. A separate Sinosauropteryx specimen contained the remains of a lizard, indicating the species had a varied diet. The Curry and Chen paper presented this as the first documentation of mammal predation by a non-avian dinosaur. Color analysis by Mike Benton, Jacob Vinther, and others in 2010 reveal the animal had a banded ginger and white tail and a darker dorsal stripe, making Sinosauropteryx the first dinosaur to have its color pattern reconstructed in detail. The protofeathers themselves are simple filamentous structures, not yet branched into the complex feathers seen in birds. They likely serve thermoregulatory and display functions rather than flight. Histology of Sinosauropteryx bone shows fast growth consistent with elevated metabolism, supporting active predation behavior. For decades, paleontologists assumed that Mesozoic mammals were small, nocturnal, and largely ignored by dinosaurs. The Sinosauropteryx find shows the opposite. A minority view has questioned whether the mammal jaws represent gut contents or postmortem associations, but the position within the body cavity supports the original interpretation. A more speculative reading suggests that nocturnal mammals were common Sinosauropteryx prey, with these specimens representing the tip of an iceberg of unrecorded predation. The species inhabited lake margin and forested environments around Cretaceous Liaoning. The holotype and gut contents specimen are housed at the Nanjing Institute of Geology and Paleontology. Number 7. The Ghost Ranch Coelophysis. Alleged cannibal or misidentified Crurotarsan. Coelophysis boreae was named in 1889 by Edward Drinker Cope from fragmentary specimens collected by David Baldwin in New Mexico. The Ghost Ranch quarry in Rio Arriba County was discovered in 1947 by George Whitaker, working under paleontologist Edwin Colbert. The quarry contains hundreds, possibly thousands, of articulated Coelophysis skeletons in a single bone bed, the largest known dinosaur mass mortality event. Possible causes include flash flooding, drought, or volcanic ashfall. Two specimens, AMNH 7223 and AMNH 7224, contain smaller skeletal material in their abdominal cavities. Edwin Colbert's 1989 monograph interpreted these as juvenile Coelophysis being eaten by adults. The cannibalism hypothesis was widely cited in textbooks for over a decade as proof that early theropods preyed on their own kind. In 2006, a study by Sterling Nesbitt, Alan Turner, Greg Erickson, and Mark Norrell re-examined the specimens with modern phylogenetic methods. They found that AMNH 7224 contained the bones of a small Crurotarsan archosaur, not a juvenile Coelophysis. Crurotaransans were the lineage that includes modern crocodilians, distinct from dinosaur ancestors. The supposed cannibalism evidence in AMNH 7223 was found to be unrelated bones lying near the abdomen, possibly post-mortem associations rather than gut contents. The Nesbitt finding does not entirely rule out Coelophysis cannibalism. The mainstream view today holds that the Ghost Ranch specimens are not evidence of cannibalism. A minority view argues the broader behavioral question is still open. Other theropods, such as Tyrannosaurus rex and Majungasaurus, do show clear evidence of cannibalism through tooth marks on conspecific bones. A more speculative view holds that future Ghost Ranch specimens, examined with CT scanning and trace element analysis, may yet confirm cannibalism in this taxon. Coelophysis lived during the late Triassic, around 215 million years ago, in the Chinle Formation. The animal was a slender bipedal theropod about 2 to 3 meters long with a long neck and tail. Coelophysis is the New Mexico state fossil. The Ghost Ranch site is now part of a museum and conference center, with active fossil preparation labs. AMNH 7223 is housed at the American Museum of Natural History in New York. Number 8. Cretoxyrhina mantelli. The Ginsu shark that swallowed a Pteranodon wing. Cretoxyrhina mantelli was named in 1843 by Louis Agassiz based on isolated teeth. The popular nickname Ginsu shark was coined by paleontologist Mike Everhart in reference to the Ginsu kitchen knife brand and the slicing edges of its serrated teeth. Adults reach 6 to 7 meters in length, comparable to a modern great white shark. The species inhabited the western interior seaway during the Cenomanian to Campanian, around 100 to 80 million years ago. A specimen recovered from the Smoky Hill Chalk of Kansas contains a Pteranodon wing bone with embedded shark teeth. Pteranodon was a large flying reptile with a wingspan of 6 to 7 meters, the most common pterosaur of the western interior seaway. The wing bone in question is a humerus, the most diagnostic and frequently preserved part of pterosaur fossils. The find was described by Mike Everhart in 2005 and is among several documented cases of Cretoxyrhina pteranodon predation. In his book Oceans of Kansas, Everhart documented at least 7 pteranodon specimens with Cretoxyrhina bite damage. The interpretation is direct. Cretoxyrhina lunged upward from below and grabbed a Pteranodon resting on the surface of the water, the shark's serrated teeth embedding in the wing as the pterosaur was dragged down. Some researchers prefer a scavenging interpretation. The Pteranodon may have died first and floated, with Cretoxyrhina merely consuming the carcass. The mainstream view, supported by the bite mark distribution and the embedded teeth, leans toward active surface predation. A more speculative view proposes that Pteranodons fed on fish near the surface and were caught by Cretoxyrhina mid-strike, in a moment of predator-on-predator opportunism. A modern analog is the great white shark attacking surface-resting seabirds. Cretoxyrhina also preyed on Scipionyx fish, mosasaurs, plesiosaurs, and elasmosaurs. The shark's tooth enamel is preserved in serrated, slicing form, capable of cutting through flesh and bone. Cretoxyrhina went extinct during the Campanian, possibly outcompeted by the rising mosasaurs and Squalocorax sharks. The bunker Cretoxyrhina is one of the most complete Cretoxyrhina skeletons ever found. The Smoky Hill Chalk member of the Niobrara Formation has produced thousands of marine reptile and shark fossils since the 1870s, with collectors including George Sternberg, Samuel Williston, and Edward Drinker Cope. The Pteranodon humerus with Cretoxyrhina teeth is housed at the University of Kansas Natural History Museum. Number 9. Tylosaurus proriger, the mosasaur with a bird and a smaller mosasaur in its gut. Tylosaurus proriger was described in 1869 by Edward Drinker Cope from specimens collected in Kansas. The genus name means knob lizard in reference to the long bony rostrum extending past the front of the teeth, which the animal used to ram and stun prey. Adults reach 14 meters in body length, making Tylosaurus one of the largest mosasaurs ever to live. The species was the apex predator of the late Cretaceous western interior seaway, alongside Cretoxyrhina, during the Coniacian to Maastrichtian, roughly 86 to 70 million years ago. A famous specimen collected by George Sternberg from the Smoky Hill Chalk of Kansas in the early 20th century, around 1918, contained a triple prey gut content. Inside the mosasaur's stomach lay the bones of a Hesperornis flightless diving bird, a Bananomeus teleus fish, and a smaller Clydastes mosasaur. Hesperornis was a flightless toothed bird that hunted by diving into the seaway, propelling itself with powerful hind legs. Bananomeus was a tarpon-like teleos reaching 2 meters in length. Clydastes was a smaller, slimmer mosasaur, typically 4 to 6 meters long, distinct in body plan from the larger Tylosaurus. Russell and others reanalyzed the specimen in 2010, confirming the original identifications. Dental marks on the Hesperornis bones suggest the bird was actively grabbed by Tylosaurus rather than scavenged. The triple prey gut places Tylosaurus among the most diverse known marine reptile diets, just behind the four-prey Prognathodon. The diversity of prey in one stomach indicates Tylosaurus fed continuously and was not specialized on any single prey type. Mosasaurs are now known to have given live birth. Embryonic Tylosaurus fetuses have been recovered from preserved adult skeletons, confirming ovoviviparous reproduction. Some researchers have proposed that Tylosaurus may have been more migratory than previously thought, moving along the seaway with prey populations through the year. Others argue for a more sedentary, ambush-based hunting style. A more speculative interpretation suggests Tylosaurus engaged in cooperative or pack hunting, similar to modern killer whales, though direct evidence remains absent. The Smoky Hill Chalk has yielded over 20 Tylosaurus specimens, making Kansas a global center for mosasaur paleontology. Sternberg's specimen is housed at the Sternberg Museum of Natural History in Hays, Kansas. The bunker Tylosaurus at the University of Kansas is one of the largest mounted Tylosaurus skeletons in the world. Number 10. Compsognathus longippus with a Bavarisaurus lizard. Compsognathus longippus was named in 1859 by Johann Andreas Wagner from a specimen collected in the Solnhofen limestone of Bavaria, Germany. The species name means elegant jaw, long-footed in Greek. The German specimen, BSP AS156-3, is approximately 90 centimeters long, the size of a turkey, with the slender bipedal proportions and long tail typical of small theropods. The fossil dates to the late Jurassic, Tithonian stage, around 150 million years ago. Wagner noticed something strange about the abdominal cavity. Inside it, articulated and intact, lay the skeleton of a small lizard. The lizard was identified as Bavarisaurus, a fast-running terrestrial reptile adapted to the dry coastal lagoons of the Solnhofen archipelago. The articulation of the Bavarisaurus skeleton indicated that Compsognathus had swallowed it whole. This was the first documented case of stomach contents in any non-avian dinosaur. It essentially founded the field of trophic paleontology. Until 1859, the diets of dinosaurs were inferred entirely from tooth shape and skeletal proportions. After the Compsognathus discovery, direct evidence of predation could be reconstructed from the fossil record itself. A second Compsognathus specimen was discovered in 1972 at Cannes in southern France and contained similar gut contents. John Ostrom restudied the original German specimen in 1978, modernizing the understanding of Compsognathus ecology and morphology. The animal was originally proposed as a possible link between birds and dinosaurs before Archaeopteryx took over that role. Compsognathus is the type genus of the Compsognathidae, a family that includes Sinosauropteryx, Sinocalliopteryx, and Guizhouichthyosaurus, the same Chinese feathered theropods featured earlier in this video. The connection between these species, separated by 60 million years and 7,000 kilometers, is a single feeding behavior: small, fast, opportunistic predators swallowing prey whole. Some early 20th century researchers questioned whether Bavarisaurus was a genuine gut content or a coincidentally associated fossil, but modern re-examination has supported the original interpretation. A speculative view holds that Compsognathus may have specialized in fast-running lizard prey, given the proportions of its limbs and the speed required to catch a Bavarisaurus. The German specimen is held at the Bayerische Staatssammlung für Paläontologie und Geologie in Munich. The Cannes specimen is held at the Muséum National d'Histoire Naturelle in Paris. Together, they represent the longest-running stomach contents case in the history of paleontology, a fossil that has stood up to 150 years of scrutiny. Stomach contents are vanishingly rare in the fossil record, and understanding why requires looking at the chain of conditions necessary for preservation. A predator must die and be buried within hours of its last meal, long enough for the prey to remain in the gut, short enough to prevent complete digestion. The burial environment must be anoxic, lacking the oxygen that fuels decay and scavenging. Mineralization must outpace digestive processes, replacing soft tissue with phosphate or carbonate minerals before the prey is dissolved into chemical residue. No scavengers can disturb the carcass before burial. Each of these conditions on its own is uncommon. The combination is staggeringly rare. For every gut content fossil that survives, hundreds of thousands of specimens preserve no internal evidence at all. The fossil deposits that produce these finds are called Lagerstätten, German for storage places, and they share specific environmental features. The Solnhofen limestone of Germany was a series of stagnant tropical lagoons. The Yixian and Jiufotang formations of Liaoning were lake systems repeatedly buried by volcanic ashfalls. The Pietrargia Plattenkalk of Italy was a coastal lagoon with anoxic bottom waters and fine carbonate sediment. The Smoky Hill Chalk and Bearpaw Formation of North America were quiet marine sediments laid down in calm, deep water. The Guanling Formation of southwestern China preserved Triassic marine reptiles in carbonate platform settings. Each represents a specific combination of low oxygen, fast burial, and minimal scavenging. Outside Lagerstätten, gut contents almost never survive. Coprolite analysis, the study of fossil dung, runs as a parallel discipline to gut content analysis. Coprolites preserve the digestive output rather than the contents, and they are far more common in the fossil record. But coprolites lack the dramatic immediacy of a predator dying with its meal still inside. Modern techniques have transformed gut content analysis. CT scanning reveals contents hidden inside bones or stone matrix. Mass spectrometry detects organic residues and identifies prey species through chemical signatures. Synchrotron radiation tomography produces three-dimensional reconstructions of internal structures invisible to the naked eye. These tools have not only validated old finds but uncovered new gut contents in legacy specimens that had been on museum shelves for decades. The fossil discovery rate for stomach contents remains roughly 1 in tens of thousands of specimens, even in Lagerstätten. The geographic distribution of gut content fossils maps closely onto the world's known Lagerstätten. The Yixian and Jiufotang formations of Liaoning Province, China, have produced the largest concentration of gut content fossils anywhere in the world, including Sinocalliopteryx, Sinosauropteryx, and Microraptor, all preserved by repeated volcanic ashfalls into shallow lakes. The Solnhofen limestone of Bavaria gave us Compsognathus and Archaeopteryx, preserved in anoxic tropical lagoons. The Pietraroggia Plattenkalk of Italy gave us Scipionyx, preserved through phosphate replacement in fine carbonate sediment. The Smoky Hill Chalk, member of the Niobrara Formation in Kansas, yielded Tylosaurus and Cretoxyrhina, preserved in quiet marine sediments laid down across the western interior seaway. The Bearpaw Formation of southern Alberta gave us Prognathodon, preserved in similar marine conditions on the northern reach of the same epicontinental sea. The Guanling Formation of Guizhou Province in southwestern China gave us Guizhouichthyosaurus, preserved in Middle Triassic carbonate platform deposits. The fossil hunting tradition in these regions runs deep. The Solnhofen quarries have been worked since the 17th century, originally for lithographic printing stones, and dinosaur fossils have been emerging for over 150 years. The Smoky Hill Chalk was first explored by Sternberg, Williston, and Cope in the 1870s and continues to yield major specimens. The Liaoning beds are a more recent phenomenon. Major fossil discoveries began in the early 1990s and accelerated rapidly through the 2000s. The Pietrorojia site has been worked sporadically since the 19th century, but modern preparation methods have dramatically increased the scientific yield. The Bearpaw Formation has produced major mosasaur specimens for over a century, with the Royal Tyrrell Museum holding many of the most important. The Guanling beds are the youngest contributor, with major Triassic marine reptile finds emerging from the late 1990s through the present. Each new discovery in these formations brings the possibility of new gut content data. The sites are not exhausted. Modern collection and preparation methods are accelerating the rate of significant finds. Across the 10 cases described, a clear pattern emerges in prehistoric predator behavior. Sinocalliopteryx swallowed prey 1/10 its size whole and was capable of consuming multiple birds in a single meal. Microraptor swallowed mammals, birds, and fish whole or in large pieces, indicating broad dietary generalism. Tylosaurus consumed 3 different species in one meal, and Prognathodon 4. Guizhouichthyosaurus tore apart a prey item nearly 4/5 its own length, the most extreme predator-prey size ratio ever documented. The pattern suggests prehistoric predators were frequently more aggressive and more generalist than modern analogs would imply. Body length ratios of prey to predator, in many cases, exceed anything seen in modern marine ecosystems. The feeding strategies vary by predator size and tooth morphology. Conical teeth like those of Prognathodon correlate with crushing prey, including thick-shelled turtles and ammonites. Serrated teeth like those of Cretoxyrhina correlate with slicing through flesh and bone. Peg-like teeth like those of Guizhouichthyosaurus correlate with grip and tear feeding, where the predator holds the prey and tears off chunks. Modern analogs are useful but limited. The Komodo dragon swallows prey whole in a manner reminiscent of small theropods. The great white shark slices through prey in a manner reminiscent of Cretoxyrhina. The killer whale dismembers large prey through coordinated tearing in a manner reminiscent of Guizhouichthyosaurus. None of the modern analogs match the dietary breadth shown in single-meal records like the Prognathodon 4-species buffet. Some researchers argue that prehistoric food webs were genuinely more interconnected than modern equivalents, that the absence of certain modern competitive pressures allowed apex predators to consume a wider range of prey. Others argue that modern food webs would show similar diversity if we could examine the contents of every individual predator's stomach in real time. A more speculative view proposes that elevated atmospheric oxygen levels in some Mesozoic intervals allowed for higher metabolic demands and therefore more aggressive feeding behavior. What remains beyond dispute is that active hunting and gorge feeding were common across diverse prehistoric predator groups. The prey completeness in many specimens rules out pure scavenging. The acid etching patterns in others indicate active digestion at the moment of death. The history of gut content interpretation is also a history of reinterpretation. The Ghost Ranch Coelophysis cannibalism case is the most prominent example. Edwin Colbert's 1989 identification of juvenile Coelophysis in adult abdominal cavities was overturned by Sterling Nesbitt and colleagues in 2006, who showed the supposed juvenile Coelophysis was actually a small Crurotarsan archosaur. The mainstream view today is that Ghost Ranch cannibalism is unsupported by the legacy specimens, though the broader behavioral question remains open. Other theropods, including Tyrannosaurus rex and Majungasaurus, do show clear evidence of cannibalism through tooth marks on conspecific bones. The Microraptor mammal foot is another case in active debate. Some researchers interpret the articulated foot as evidence of active predation. Others argue it could represent scavenging from a larger predator's kill. The articulation and intact claw sheaths support active capture, but scavenging is not ruled out. CT scanning, mass spectrometry, and trace element analysis are increasingly being applied to legacy specimens to test old interpretations. Some cases have stood up to a century and a half of scrutiny. Compsognathus, with its Bavarisaurus lizard, for example, has not been seriously challenged since 1859. Others have been overturned within a decade or two of being established. The trend in the field is toward greater caution about identifying gut contents in older specimens, with stricter criteria for distinguishing genuine stomach contents from post-mortem associations. Bone position relative to the gut cavity matters. Surface etching consistent with gastric acid matters. Articulation versus disarticulation tells the story of the digestion stage. Some fossils have been reprepared with modern methods to expose features that were obscured by older preparation techniques. Early 20th century preparations sometimes damaged specimens by removing matrix that contain important contextual information. The reinterpretation process is not a criticism of earlier paleontologists. It is a feature of a self-correcting science. The original discoverers worked with the methods available to them. A more speculative position within the field holds that many additional gut content cases remain to be identified in legacy specimens, simply waiting for someone with modern tools to look again. Stomach contents are time capsules. They preserve single moments, a predator's last meal, in a way no other fossils can. Bones tell us what an animal looked like. Teeth suggest what it might have eaten. Trackways show how it moved. Stomach contents capture an event, a specific meal at a specific moment, frozen forever in stone. They give us access to behavior that would otherwise be invisible from the fossil record alone. They show that prehistoric predators were not slower or less capable than modern ones. In many cases, they were more extreme. The Triassic seas held kaiju eats kaiju ichthyosaurs that tore apart prey 4/5 their own length. The Cretaceous seas held mosasaurs that consumed 4 entirely different species in a single meal. The Jurassic forests held Compsognathus, the founding case, with a complete lizard articulated inside its abdomen. The Cretaceous forests of Liaoning held Sinocalliopteryx eating 2 birds and a fellow feathered theropod, Microraptor eating mammals, birds, and fish, and Sinosauropteryx eating multiple mammal species. The Cretaceous skies above Kansas were patrolled by Cretoxyrhina, an apex shark that grabbed Pteranodons from the surface of the seaway and dragged them down. The Cretaceous mosasaur Tylosaurus ate flightless diving birds, smaller mosasaurs, and tarpon-sized fish in single meals. Each of these moments connects the modern viewer to deep time in a way bones alone cannot. Without Lagerstätten, the rare fossil deposits that capture soft tissue and gut contents, food web reconstruction across deep time would be largely impossible. We would still know what species existed, but not how they interacted, what they ate, what ate them, how often they fed, how aggressively they hunted. The 10 cases here represent only a fraction of what has been recovered. New finds emerge every year as fossil collection accelerates and modern analytical methods are applied to legacy specimens. Future discoveries will overturn current interpretations, just as past interpretations were overturned by new evidence. Each fossil is irreplaceable. Once damaged or destroyed, it cannot be replicated. The Lagerstätten of the world are non-renewable scientific resources. The protection and careful study of these sites, Solnhofen, Pietraroggia, Liaoning, Kansas, Alberta, Guizhou, ensures that future generations will continue to read the moments of deep time captured in stone, the precise instance when a predator made its final mistake and was buried with the evidence of its last meal still inside.